Okay, after hearing Karen's talk, I realized that some things I was going to say would kind of overlap with what she said, so I'm switch some things around so that I wouldn't do that. But I did want to add one thing, which is, just to echo one of the things that she said about the sensitivity of, particle contacts. And this was one experiment that just, I always found astounding that we did. So the idea was along the lines of what Karen was telling us about sending sound waves into a granular pack. And so this is a picture of the apparatus. And so it's you have a speaker. The speaker goes inside the cell. This cell is basically this big. It's filled with particles that are on the order of half a centimeter, 5 millimeters. So the big macroscopic particles. There's a plunger here with the speaker so that it's shaking. And we know how much it shakes because we have a transducer on the back. And we have a pickup in the front. So this is what we're doing. We're just sending the sound in and measuring how much sound gets from here to this point in front of it. And off to the side here, we have something else. And so this is just a little carbon resistor. So we shaved it down so that it was smooth and it was on the size of basically the same size as the particles themselves. And so what was the point of the carbon resistor? Well, if you pulse the carbon resistor and you put a pulse of current through it, its temperature is going to rise. And so temperature rises. You can figure out how much it rises because you put I squared R, so you can figure that out and find out how much the temperature rises. And what we did was we pulsed it so that the temperature rise was around 1 degree Kelvin. I mean, it's at room temperature, so maybe 1 degree centigrade, I should say. But it's not. It's 1 degree. And what does that mean? Well, that means that that particle expands on the order of the thermal expansion, which is 1 part in 10 to the fifth, right? That's per degree. That's roughly the thermal expansion of particles. So what we're doing is we're taking one particle, it's kind of off to the side here. We're pulsing it by 1 degree, which is changing its size by 1 part in 10 to the fifth. It's not even in the line with where we're picking this thing up. And this was what the signal looked like. So here was the signal before we did any pulsing. You pulse it, and it dropped by 25%. So just this one particle out of 100,000 particles in the system, changing its single size by 1 part in 10 to the fifth, gave you a drop of 25%. And then you can watch this thing recover. And so this is the thermal diffusion in the system as this thing all equilibrates. And it's reversible. It goes back to itself again, to where it started. And so you can do it again. And so I just wanted to show this to kind of echo what Karen was saying about how sensitive these things are to these incredibly small changes in something in the problem. Now, the other thing I should just say, it isn't anywhere in here. That is, if I had put another heater over here, for example, or right next to it, it might not have given this kind of a big effect. And so the effect changes from position to position to position throughout here, and that has to do with something about whether it's on a forced chain or not a forced chain. And so that was kind of the interpretation, much along the lines of what Karen just said. And so I just wanted to show that because I thought that was, to me, an astounding thing, just backing up her the points that she was making. Okay, so what I want to talk about now is another topic. So going back, and this I think has to do with this idea that I was asked to talk about experiments in marginality. And this, to me, I think was the first experiment that really was trying to probe marginality. And it wasn't in a soft matter system. It was a hard condensed matter system. And so this happens in charge density waves. So how many people know what a charge density wave is? How many people have no idea? OK, that's what I figured. So what is a charge density wave? It's a wonderful thing. It's basically, I mean, have you heard of Peierls instability? No, OK, that didn't go anywhere. OK, so I won't try to explain where it comes from, but it's just the following thing that happens in here. It's a nonlinear effect in certain quasi-one-dimensional conductors. And so niobium triselenide, for example, is one example of this. And what it is that there's a mode of conducting where all the electrons in the system move together if the voltage pushing on it is greater than the threshold. So it isn't that you turn on a little bit and it moves a little bit. It's nothing, nothing, and then suddenly the whole thing starts to move at the point where you pass the threshold voltage. And so this was something that was discovered in experiment, and it came on the pulse duration memory. Okay. And I want to describe what this is. Okay. So the idea is that if I have this system, I can plot the voltage that I put onto the system, the leads across this thing. So I have basically the system is, I put a current through here, and I measure the voltage. Okay, so it's just a simple, I'm just measuring the resistance of this object, and I can measure the voltage, I can measure the current separately. And you can control one or the other, but you control one of them. OK, so if I put the voltage on the way I described it to you, I start off, there's 0 voltage. I put a voltage on this. It's above this threshold. So this is the V threshold. And so nothing's going to happen before I put the voltage on. And then once it passes that threshold, the current will start to flow. And so if I plot I versus t, what I'm going to see here is that there's no current. And then suddenly, at the same point, it'll start to rise. And at this point, it'll go away. And it'll do something in the middle between those 2 points. And it starts and it stops where the current, where the voltage goes above and then below the threshold. And so what the experimentalists did, and this was 2 groups, Lynn Schneemeyer at Bell Labs and Stuart Brown at UCLA, were the 2 groups that were doing these things roughly at the same time. So they then did it again. And I'm trying to draw these as identical voltage pulses. And so it does something else. So it goes up and it goes down. I'm trying to make this thing go down roughly at the same point that it goes down. It isn't exactly the same in the middle, but it does start and stop at the right places. OK, so of course they have, they wasn't doing this by hand. They have a signal generator that is giving these signals, and so they were just watching what happens with this. And so you do this over and over and over again. And so what happens eventually to this system? Well, you put this voltage on, and they're identical pulses. And by gosh, this system has read your mind. It figures out where you're going to, when you're going to turn the voltage off. As you could have turned it off at any point, but it figures out where you're going to turn this off, and just at the point where it's going to turn off, it does this. It starts to peak up just before you are going to turn it off. So of course, you know, saying it this way, that it reads your mind, of course, the sample did not read your mind. But what it did was it got trained to this point, so that it got trained so that it was trained so that at the point of turning this thing off, it was in some configuration that was the same from time to time to time to time. And it kind of repeats this over and over again. It's gotten to some kind of a fixed point. So this fixed point that it's gotten to is a marginal state of this system. And so this was the first inklings of, you know, at least where I first learned about marginality in this. I mean, there were all sorts of other kind of marginal systems, but we hadn't kind of thought of them in terms of marginality at that point.
Question. So what was this approximately? Well, maybe even in relation to what time you tried that.
Pardon? So this was in the, let's see, do I, 1986.
And the other question is, so how many pulses does it take to train?
That was not something that they were particularly interested in. They just, you know, let it run, and then it kept doing this when on the output. I mean, so
But the early ones are not showing.
the early ones are not showing it, and the end ones do. And so just to show you what this looks like, this is the data. So this is the two groups that I told you about. And these are the different times that they showed. And you can see each one of these, just at the point that you're turning the voltage off, the current rises and then gets cut off. And so it does this. It somehow has trained the system, and it's gone to some point. And so this is, you know, kind of a beautiful thing in the sense that, well, gee, how does this weird system train itself? And this training is, I mean, where I'm going with this in this thing is that this training is a kind of a memory in the system. That is, it may not have been how they were trying to talk about it at the time. Well, they did. They called it pulse duration memory. This was, but some of the where I'm going with this is to say, oh, well, memory formation is part of what's kind of important for disordered media, and that's one of the things I want to kind of get across. I also want to get across that this came from experiment. I mean, so you know, just so that, that's why I'm up here. That's the only reason I was invited, is because I like experiment. Okay. Was there a question? No. Okay. So how do you think about this? And so what I wanted to, you know, to start this thing off, what do I think about this? So I want to think about this. Okay, these are memories, and I want to think this more generally about memories in matter. And some of you, I think, may be at the, there's going to be a program at KITP in Santa Barbara next January, which is going to explore these ideas of memory and matter generically. I mean, not just this kind of thing, but all the different kinds of memory. And what I want to, so what would, so having told you this, back off for a second and say, well, suppose I have a memory. What are the things that you would think should make a memory a good memory? I don't mean pleasant memory. I mean a good, you know, that you robust, that you understand, that will last. And so a couple of things that I would have said was that if you repeat it often enough, that is, how do we learn in school? We learn by rote memorization, and so you learn over and over and over again, and so lots of repetition. Okay, so that's one thing, and so that should make a good memory. Lots of repetition. And another thing that I would think would make a good memory is, well, it shouldn't be a very noisy environment. So, no noise. And so what I want to describe to you today is a kind of memory where I can give a system, a material, many different inputs, and it will remember all of them. So my memories, the ones today, give many inputs, that has many of these different lengths in this thing, and it remembers all of them. That is, the memory has all of those inputs. But after a while, it forgets everything. But one. So now you can see why I kind of like this kind of memory. I mean, it describes me exactly. I can only remember, old stuff. I can't remember anything new anymore. I mean, even though you tell me your name 100 times, I can't remember it. I only remember my parents' names. I mean, that's basically what I'm reduced to. Okay, so it does this. Even though you just told me the name, I can't remember it. Okay, and then the third thing about these memories is that, however, if I put noise in, then it remembers everything. Okay, so exactly the opposite of those two things I told you. Lots of repetitions makes memories bad, and noisy environments makes memories good. So it's exactly the opposite of what I naively expected. And I'm presenting it to you in this way so that I hope you say, oh, that's odd, that's strange. I mean, is it strange? Yeah, okay, thank you. It's strange. But by the end of this, I hope you say, oh, well, it's obvious, right? That's the purpose of this. It's not trying to make it funny, but there's a very simple way of looking at this that says, oh, this is a new kind of a memory or a different kind of memory that should somehow be robust. Okay, so it has to do with these charge density wave systems to begin with, and this is where we first found it. And the way you understand something about these charge density wave systems, which I'm not going to go to in much detail, was done by Coppersmith. So Sue Coppersmith and Peter Littlewood. And so the way people used to model these charge density waves was what's called the Frankel-Kontarova models. Some of you may know that it's a high-class theory model, which they loved. I mean, at the time. Everyone did that. And so what is this model? You have a very large potential, and you have masses sitting in these in various wells, but these masses are connected by very weak springs. And so there are a lot of masses and a lot of wells, and they're not all nearby wells. There are, there's a lot of space between these things, and these springs have spring constant K. And so you can ask, what are the forces on any mass? And so this is the masses are basically supposed to represent the defects in the crystal. The oscillating potential is supposed to represent the charge density wave, which is and the spring is the how the charge density wave basically is being distorted by the by trying to match with where the particles are. And so in this case, the particles move rather than the wavelength changing, but that's the idea. And so you can calculate what the forces are on this. The forces are just going to be the spring forces, right? We know how to calculate the spring forces on any particle. It's going to be minus K times, K times 2 delta Rn minus delta Rn minus 1 minus delta Rn plus 1. Right? It's just a force on the spring. And then what is the idea of the electric field? What the electric field does is it just tilts this whole washboard. Right? So it tilts this washboard, and everything gets to flow, but it only tilts it for a while. It only flows for a certain distance, and then you bring it back. And so this was the model that they used to try to analyze this. And that is able to show, it's a very beautiful model that allowed you to see why you get this kind of pulse duration memory. That is, at the end, once this thing has reached its fixed point, the particles are always just poised at the top of a potential well because they have stretched as far as they can in that time. I'm not going to go into that here so much, just so that I can get to the other stuff. That chalk is terrible. Do we have, where's my favorite yellow chalk? Here it is. Okay, yellow chalk. Okay, so what we asked at that point was, okay, so suppose you have this, and we started with this kind of model. Suppose we have this. Suppose I gave it 2 pulses. Instead of just giving it a pulse of time A, and do it, I give it 2 pulses, A, B, A, B, A, B, over and over and over again. So I'm giving it 2 pulses over and over and over and over again. Can it learn those? If I give it 3 pulses, of different durations, A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D, over and over and over again, at the end of the day, can it remember all A, B, C, and D? And let's see, that's the next. So I think that's there's the model. So this is just what I wrote. The spring constant and then the force in the field is this. And now we put on A and then A1, A2, A1, A2, etc. And this is what the system remembers. So you started off at the very first cycle. It remembers nothing because there's nothing to remember. Then after 20,000 cycles, it has peaks. I'm not telling exactly what the peaks respond to, but they are the memory of those inputs. and it can remember all 5 of these inputs. After 45,000 cycles, those peaks are getting stronger and stronger. It remembers all of these things even better. So I'm remembering many inputs, and they're being repeated. But then, of course, I keep going, and what happens? Well, after 60,000, all of these peaks start to decrease, and at 230,000, there's nothing left in the middle. You only get the largest and the smallest peak coming out again.
Yeah, but you didn't say when the peaks are remembered, well, when the peaks do appear in between, before it forgets, you stop driving it, or like, why do you call it a memory?
Because I can look at the cycle at that point and see, it's peaking up at the end. That is, you can watch how those. So I didn't tell you how I go from here to that. I mean, that's a somewhat different measure. It's a theory measure, and this was the experiment. But those peaks correspond to the fact that this system has a peak at the end. Okay, so that's what it's, and in this intermediate time, I'm able to see those peaks. That's what these peaks are showing. And then you keep watching how this train of pulses evolves, and all the middle ones go away. But then, if you put noise on, do I have it? No, I don't know. But if I put noise onto the system, then all of these peaks return.
So what's the difference between the last 2 versus the middle one in terms of the experiment?
So this would have to do with something about the longest and the shortest, but it's a little bit different from that, and I'm not going to. I'm trying to give you the gist of what this does. I want you to see that this is something that happens in a hard condensed matter system, and it has these 2 features that I want to say. So I don't want this to be a talk about this particular model, because I want to change it to jamming, or something like jamming. I mean, this is okay. So this is what we were able to see, and you could do the experiment on this and try to feed it many different cycles. And so this shows 2 of the cycles, and what you can see is that in each case, so we gave it 4 memories, and in each case, this one has a minimum, and this one has a maximum. This is how it depends on the sign of what you're putting in, but it was able to memorize all of these different things in the experiment. So the experiment also has this feature that it can remember all of these things. Okay, so now what I want to ask you, so this was 15 years ago or so, and I love this model. I mean, but I had no way of trying to figure out, is this just something cute about charge density waves, in which case it's a cute thing about charge density waves, or is it somehow more more generalized, more generic than that? And so that's what I want to ask you. So are there other systems that display this? And for a long time we couldn't think of any. And then once we thought about something in a slightly different way, we were able to see how you could generalize this. And so this is what I want to tell you about now. Okay, so what I want to think of as a soft matter system. So I'm going to ask you to think of a liquid in a box, a very, 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 very viscous liquid. And this very, very viscous liquid has some particles in it. Okay, so a whole bunch of particles. So there are They're not touching each other. I'm not at the jamming transition. I'm way below the jamming transition, but they are not touching each other. And then I want to shear this box. And all these particles have to shear with the global shear in the system. And if I do this, these particles will move. But if I only shear by a small amount and bring it back to where I start, so then I'm going to return to this. This configuration of all the particles, which I can now visualize, I can take a picture of that, they should come back exactly to where they started. Okay, so there's a, the reason I say that is, how many people have seen the YouTube version of where G.I. Taylor takes a very viscous fluid and puts a drop of ink in it, and you stir it up, and it goes away, but then you take it back, and it all comes back to itself. Right? So lots of people have seen it. So I don't have that here. The last time I took the demo with me, I got crucified at the airport because glycerol was the liquid, and nitroglycerin is nitroglycerin. And so we were, I don't do that anymore. But anyway, this is just a theorem in fluid dynamics, right? That is, if you have very, very viscous flow, very, very, very low Reynolds number, liquid will return exactly to its initial conditions if you change the boundary conditions back along the path in which you came. So this was an experiment that was done by David Pine and Jerry Golub. And what they found was this, that this is kind of true. So if I don't shear this too much, this really does come back exactly to where it started. So the experiment was the following. You have this fluid, you put all the particles in it, you shear it, you bring it back, and you take a picture, pop. And then you shear it, you take it back, you take another picture, pop. So that you're strobing this just at the same point in the cycle each time. And so now you've come back to where you started each time, so the particles, if they really returned and they were totally reversible, would come back exactly to where they started. But if you shear too much, then these particles start to interact with one another in a way that doesn't get reversed by time. And so they come back and they're off a little bit. And you do it again, and they're off a little bit more. And so what you see for larger amplitudes is that each of these particles starts to diffuse a bit because they interact, and now they move to a new place, but then they come again and they interact again. But what they found is that for this intermediate range of amplitude, after a while, it found a place where all of these particles ended up where they were at the cycle before. Not where they were where you first put them in, but they learned this after this cycling through. Okay, so this is basically, it reaches a steady state over here. What the idea that we had was that a steady state is a memory. So that's the first thing. So a steady state is a memory of something in the system. That is, if that steady state, the value of that steady state depends on the amplitude with which you perturbed it. And so there are lots and lots of examples of this kind. And so I've have one example here. So if you take granular material and you stick it in a tube and you shake this tube in some way, the sand will slowly become more dense. But if you shake it a little bit, it doesn't change density very much. If you shake it a lot, it changes density by a lot. And depending on how hard you're shaking it, you get to different places within. So this is my demonstration for today. This is basically just sand grains in this tube. And just to show you the basics of this effect, what I have here at the top are numbers. These are centimeters from the bottom of this container. So I turn this over, and my thumb is 24 centimeters from the bottom. And now, works even left-handed, it's now 22.5 centimeters from the bottom. That is, just by kicking it a few times, the density gets higher. It compacts. And so, depending on how you do this, you can get down to a 10% change easily in what the density is. But it depends on how hard you're kicking this each time. And so I'll pass this around, but if you make too much noise, I'm going to take it away from you. But the prize is to, I'm not saying what the prize is, but the prize is whoever gets the lowest density wins. I mean, OK, so this is an example of what I'm talking about, a steady state. At the end, you just measure the density. And the density depends on what how you've hit this thing. So if you measure the density of this at the end of the day, you will know what how much I was kicking it for as a function of time, right? So this is that example. Okay, so this is what we wanted to do in this case. And so the experiment, or the way of simulating this, is, again, we wanted to see whether this thing had a memory. And it clearly does from what I just told you. But there was a simulation that went along with that, those experiments. And this included Paul Chaikin as well, so Pine, Golub, Corte, and Chaikin. And the idea is that if you have, let's say, 3 particles, I'm sorry, so I start off here. And I have 3 particles that aren't touching. And then I shear this box so it's like this. Then everything gets distorted finely in here so that these 2 now overlap with each other because they are of finite size, so they will overlap. And then when I bring it back to its original position again, I've just kept track that these 2 particles overlapped. And if they overlap, I give them a kick. This one didn't overlap with anything, and so it doesn't get kicked at all. Okay, so it's just going to target those particles that overlap, that interacted with some neighbor. And so having said this, then you see why this is a very simple simulation to do, because you don't even have to do the shear. All you do is you know what volume and some shape associated with each sphere is going to lead to an overlap. And so you can just do this very rapidly, and you keep kicking this thing and kicking this thing and kicking this thing until they don't overlap. And so you can see what this is doing. That is, what the transient region of this is where particles are still overlapping with each other. And if they're overlapping with each other, they get kicked. And if they still overlap, they get kicked. And if they still overlap, they get kicked. And so what this is saying is that you get kicked as long as you're as long as you're interacting, you get kicked and you explore phase space. But if you ever reach a point in phase space where you no longer get kicked, then you don't move at all ever again. And so this will tell you when the system has reached its reversible place, because once it's reached reversible place, there is nothing in this simulation which is going to give rise to any motion ever again. And so you can then go and see, well, what was the memory that you encoded in here? That is, what was, you can tell that because if I now sheared this just a little bit more than the initial, than my training, it will start to interact. And once it starts to interact, then I can tell that because things will start to rearrange. And so what we did was basically the same simulation that these people did. And what I'm going to plot here is a fraction of particles that move. So its largest value can be 1. And this is the amount of strain I put on this thing. So this is gamma. That tells me how much I have strained this thing. And what's this thing going to look like at t equals 0 before I do anything? It's going to look like this. That is, it's got to be a monotonically increasing function of gamma, because if it interacted at small gamma, that interaction is going to still remain when it goes into high gamma, so this thing can only be monotonically increasing. What does this thing look like after it's reached its steady state, the final point? Well, if this is gamma 1, where I've trained it, nothing interacts until I reach gamma 1, and then it starts to increase monotonically from then on. Okay? So this is basically what they showed. But what we then looked at is, well, what happens if I only do this for a few cycles? So if I do this for a few cycles, then you see that I'm starting to clear out the region below gamma 1, but the region above gamma 1 really doesn't get changed by that much. And so you begin to see this cusp in here. And so this is for 0 cycles. This is 100 cycles. And this is infinite cycles, the final cycle. And if I go to 1,000 cycles, then it does this. It's even stronger. And so that one was 1,000. Okay, so you can read out this memory before it is fully formed by just looking at this and asking, okay, as a function of this strain, you can ask where was it, that is, without having been told where this thing had been trained at, now you just change gamma and you just see where do I start to have particles interacting with each other. You can see that once I reach gamma 1, there's a change in the behavior. And this change in the behavior is given because of this cusp in the shape of F fraction versus gamma. And that cusp becomes completely dominant at the end. And so the thing that we're going to look at is the second derivative of this curve. And so that's going to pick out these cusps. So that's the idea of what the data is going to do. OK, so having said this, now I'm going to give it 2 memories. Right, so this is gamma 1, gamma 2. I can give it gamma 3, gamma 4, then gamma 1, 2, 3, 4, gamma 1, 2, 3, 4, gamma 1, 2, 3, 4. That's over and over again. I do back over and over again. Okay, so that's the idea here. And what I want to see, so what am I going to see in the output for this F fraction? So if I plot this versus gamma, so here is gamma 1, this is gamma 2, and this is f, same thing. Well, the beginning, it's the same. It didn't know anything happened, so it's just going to be that same curve. At the end, it's also going to be trained out to here. So that's the same. But what's going to happen in this transient region? In this transient region, it's going to have a cusp here and another cusp at that point. So now I'm beginning to see two cusps in here, and I can measure both of these things coming out. So I think I have what this thing so this is was what I was trying to show what this thing looked like. This is what the data looks like. So at the beginning, I get cusps where I trained this thing at 4 different places. And this is at the very first cycle. So it's just beginning to try and remember something. After one cycle, remembers just a little bit. I'm measuring that the second derivative of that. So it's measuring how cuspy that shape is as a function of the strain amplitude. After 1,000 cycles, you see I measure all 4 very nicely. After 100,000, only this top one is really remembered as well. The other ones are beginning to fade. At 600,000, I don't see much at all for the lower 3. But then when I get to about 2 million cycles, this thing is basically completely flat until I reach the one memory that has remained. And so, having said that, that was what I told you, that has remembered all of these things for a while, and then forgot everything except one. And that's what this is doing. That is, this clearly shows you why at the end I can only remember one memory in the system. In between, at earlier times, before I reached this steady state configuration, I had several memories that could be remembered. Georgios. In this case, it's the biggest, right? And also, if I had actually looked at what happens the other way, there is actually 2 things remembered. One is where, that I didn't go in the opposite direction to this. And so it remembers the largest one going in this direction, the largest one going in that direction. So those are the 2 things that remain. Mike?
What are the closest strain amplitudes that you could remember, right? If they're too close, that they just get lumped into one peak? Or
No. So the largest strain amplitude, that is, what is the problem is the size of the system and how long you're willing to wait. Okay, so that is, I can remember all of these things ultimately really, really, really well if I have an enormous system where I have that resolution. But you can ask how many memories can I remember in this way? N, right? It's only the spacing between particles. And so if there are n particles, n minus 1 spacings or whatever, but that's the number that you get to remember. You don't get to, it isn't something exponential in n. It's not like the number of ground states you have in a system. It's just number of spacings that you have. Okay, so this is, yeah?
As you're doing this training, as you're repeating this cycle, can you switch the order?
Yes, that doesn't matter. That is, but at the end, even if I give small ones, it doesn't remember. So even though I just told you that small one, you can't remember it. That's the frustration of this poor guy. So what this does is I've taken memory, and I've called it a memory, and there are 2 things that are different about this memory than what we might have thought about at the beginning of the lecture, which is, on the one hand, the memory is, I'm saying any steady state that has this property will be a memory, and so the steady state is a memory itself. So that's one thing. The second thing is, what did I think of an erasure? I thought somehow erasure was going back to my original system. Somehow that's how I erase something. I get rid of everything that was there. And so now I'm back to my original configuration. But that's not what this does. Clearly, what's happened is that I'm still able to, that I'm still giving it a kick here, I mean, at this point, but what I've done, I've gone to a new state where above and below this gamma 2, it's so similar to each other, I can't read it out anymore. So it's no good to have a memory there if I can't read it out. And so what's happening in this kind of erasure isn't that it's going back to this original case, it's that you lose the ability to read it out. And so that's a second kind of erasure that you wouldn't necessarily have thought. So that's the two separate things here. And now what I want to ask is what would happen if I added noise into the system? Well, why does this go to this fixed point? It goes to this fixed point because every time I do it, I'm going closer and closer and closer to that fixed point, and I can't, once I'm at that fixed point, there's nothing I can do. That is, I have lost any ability to have any memory below that fixed point. But what does noise do? Noise is continually kicking you away from the fixed point. So no matter what happens, I'm kicking this thing a little bit, and particles then do something so that in here, I'm never really able to get all the way to 0. And so if I'm not able to get to 0, then I have the ability to train a memory in here. And so these are the two things I said, oh, this should be surprising. These were the surprising aspects. But at the end of the day, they're really kind of simple if you look at them in this way. That was what the purpose of this was.
So is noise just kicking every single particle in the system a little bit?
So you can do lots of different kinds of noise. And, what we did in the simulations was, you just have a background thermal temperature. So everything gets kicked a little bit, and you just kick them more if they are interacting. So that's, and in the charge density wave case, what we did was, if the springs got too stretched, we just broke them and reset it. And so that was a way of putting the noise into that system. But in the experiment, which I'll tell you about very briefly, in the experiment, what you have is that these particles are slowly drifting because you never get precise buoyancy matching of these particles, and so therefore they slowly drift, and that was what gives rise to the noise. Yeah?
One question about the noise. So the noise that would retain all the memories has to be some sort of like intermediate level of noise, because it's non-zero and it's not like infinite, right?
Mm-hmm.
And could that like noise at which we retain all the memories tell us like something physical about the system? Why is it maximized? Why is the memory?
Yeah, so look, this is a great question. That is, everyone wants to know, well, how much noise do I need?
Yeah.
And I don't think that there's any threshold in any of this. That is, it's a question of how big a system do you have and how long are you willing to wait and do the averaging. So I think that if you have a tiny little bit of noise, that means you have to be very, very careful, and you'll see tiny little blips at the end. So this is what happens with noise. And so these things would just be a lot smaller if there was very little noise. If there was too much noise, again, it'd be hard to pick out because everything gets kicked, but there would be still some remnant of this training in there. So all we were trying to do at this point was find, is there a sweet spot? And yes, there was a sweet spot, but actually determining where that sweet spot is a great question, and we haven't investigated that.
What's the relative amplitude of the memory in the end?
Certainly, what you're doing with the higher thing is the larger strain is you're always trying to erase the lower ones. And so what you basically see is that the ones that go away first are the lower ones. On the other hand, at the beginning, the lower ones are easier to encode. So, but more than that qualitative thing, I don't have a great answer to that.
If you go infinite cycles with two gammas, for instance, and I mean perfectly, and then add noise by displacing particles a little bit, does it recover the memory?
So it has to keep being trained, but as it keeps being trained, it remembers that. So you can, once you start moving the thing, it can start learning those memories again. They've gone up to that point. It isn't as if they're remembered, but but you can by putting the noise in, it lets you learn those memories back again. But they aren't somehow stored in the system that you had a chance to look at. I don't think I don't think there is. But it's a good question. I'm not sure. Well, shearing in the opposite directions will not affect this. It's going to affect the memory in that direction. So you can have memory this way and then the maximum in that direction. So they're actually, at the end of the day, I've only plotted in the forward direction. There's a memory here, and there will be a memory in the negative gamma direction too. So that, again, just like the charge density waves, there are two memories for the largest and smallest. Okay, so and then so can you see this in an experiment? And so okay, so that's that. And so yeah, so this is the kind of experiment that you do. And so this was you have a cylinder on the inside, which is what you're going to rotate back and forth. You have a thin gap where you put your fluid and the particles in it. You use a laser sheet to illuminate those particles, and you have them index matched and buoyancy matched, and then you have fluorescent particles so that you can, or in this case, you have the fluorescent dye in the fluid, and so you can see by the black spots in that sheet where the particles were, and so then you rotate it, bring it back, and take a picture. Rotate it, bring it back, and take a picture. And so this is the kind of thing you get lots and lots of particles. You see all these little dots all over the place, and then you overlay the first picture with the second picture, and you see how many of those dots are in this, how much overlap is there between those two images. The second and the third, you do the same thing over and over again. So this is how you do these experiments, and they are not particularly trivial. What you want is to have a very viscous fluid so that you're in this Stokes regime, that is the low Reynolds number regime, so that that theorem is basically satisfied that I told you before. And depending on what your volume fraction is, it just tells you how much you're able to shear this thing. That is, if you go to very, very high volume fraction, you can't shear it much at all before you get into the irreversible regime. And the hardest thing, which was the bugaboo of this experiment, was the fact that we have noise that we can't really get rid of very easily. And that was because these particles, we have 3 different fluids that we're trying to buoyancy match these particles with, and they're never perfect. And so these things are slowly drifting. And it's that drift in the time scale of the experiment which is what gives us the noise that we can't get rid of. And so we have to try and, it isn't, yeah, so that's the problem. And then this is just, I'm not sure, having told you this, I can show you the data, but I don't think this is going to be terribly useful in the sense that, okay, so now you've seen what the experiment is like, and yes, we can reproduce these things in the experiment. And so I will not go through that. But what I do want to say is, okay, so one thing that is not clear, and so what I've kind of made it, I hope, very simple. What is the idea behind this is very, very simple. That is, it's just this thing managing to find a fixed point. If there's noise, it can't find that fixed point. And on the way to that fixed point, there can be lots of other fixed points that it remembers transiently as it gets there. And so that's why you had those strange things about it keeps all the memories for a while, but then forgets them. And with noise, it remembers everything. And so that I hope this somehow shows you why this thing kind of is a generic feature. It's not something that's really special about charge density waves. It's seen now in a non-Brownian suspension as well. Sorry.
With sort of a general claim of how many memories or how much information can be encoded?
So I was trying to say that before. There's at most n. There's let's see, for a one-dimensional string. It's at most n because all you've got is a spacing between adjacent particles. So n minus 1. But so it's not a lot of memories, but n is more than the Hopfield memories. So it's so if you've got a lot of n, you've got a lot of possible memories. I mean, I'm not sure you would want to get things close to n to be able to resolve anything, but that's the upper bound, clearly. Okay, so what I want to now just quickly say is why does it remember anything of the earlier memories? That is, there are a lot of other systems which, if you can put a memory, let's say in a magnet, and you train a magnet up to a certain field, and it remembers that field to which you've done it. Those are the hysteresis loops that you have in a magnet. But if you go any higher than that magnetic field, you've erased all the information about where the smaller hysteresis loop is. So you can only remember things smaller than the last one you put in. Why is this different? And so there's a way of looking at this on a one-dimensional line where I have put particles down at random, and the picture is that these start off as little dots, and these little dots then each cycle they swell to a certain radius and then shrink again. They swell to that certain radius and shrink again. Each time they try and kick each other apart some way. And so at the end of the day, you will have particles that are just touching when, for let's say your smallest memory. What happens when I now put a larger strain on this? So I have this memory encoded at the smaller value. What happens at the larger value? Well, all of these guys now get kicked. But the ones in the center get kicked from both directions. They can't really move. Their density is still conserved. So the only thing that can happen is the particles at the end move. And that's a slow process. So what's happening is that you can create these memories locally, but to destroy the memory needs evaporation from the edges. And so this evaporation from the edges is why this is a slow process and why it doesn't get erased immediately and why you still get to see both things in here. Okay, so this is this kind of memory. And it's I think somewhat robust. You can see that the memory now is not stored globally. It's really a local thing. That is, it's what do neighbors see. And those neighbors see, so it's kind of like a hologram. That is, if I cut out a little bit of the system, it would have the memory maybe not as well precision, but the memory would be there. And it's just better if I have all of it. But I don't need all of it to see the memory. So it's stored locally in this thing. It's also, the main thing about this is memory stored in the dynamics of the system. So it's, in that sense, inherently different from these memories that you may have heard about in neural networks, where you ask it to store memory, and what you do is you just put it in the place you want to store the memory and let the connections evolve over time so that that becomes a particularly deep well in the system, in your typical greedy algorithm to create a memory in that kind of case. Here, it doesn't help that I just sheared the system and let it sit there. That does nothing for it. It's only the fact that it went back and forth along this path. So it's in the dynamics that this memory gets stored. And so I guess for this part, I should say, the one last thing I want to say is, well, what happens now if you go to the jamming case? So now we increase the density. And I increase the density so much in the system so that the particles are always in the jam state. They can't, it's a rigid system, but it's a rigid system with soft particles, and so I can shear this soft particle system, and I can watch whether these particles stay in the same state, or if I put it far enough apart, that's if I shear it enough, the system will evolve to a new ground state after I've sheared it. As it goes over energy barriers into new states as I shear the system. Suppose I now do that and I shear it back. Will I get to the same place? And no, there's no reason that you have to go back. Once you go in the forward direction, you don't reverse yourself when you go back if you're going over energy barriers, because there are going to be other energy barriers that will take you to a new place. And then that new place is not the same as what you get in the old place. So for example, even in a one-dimensional case where I just have two barriers that look like this, going in this direction, and then where I've started over here, and I get over to this point after shear. If I move backwards, once I get to here, I don't get into the same place anymore until I've gone so far in the backward direction that I've come into this case. That is, you have to, once you have the energy barriers in the situation, in the problem, things get much more complicated. What I want to show here just at the end is, so now these are simulations on jammed systems where we are not doing multiple memories, we're just doing one memory. And so this is also, there's work that's by Sri Sastry that looked at this as well, and maybe some other groups, but Sri's papers that started us off on this, was to look at the energy. There's the enthalpy as a function of cycles. So this is as formed, and you just start shearing it in one direction and back. You're just going back and forth in the same cycle over and over and over again. And you see that at the beginning, you go over one barrier and another barrier and another barrier and another barrier, and at the end of one cycle, you're at some other place. And you do this again, and you get to another place. And you do it again, and you get to a third place. And then you do it a fourth time, and suddenly this thing becomes independent of time. That is, it repeats itself over and over and over again. It's not reversible. That is, going in this direction is not the same as going back, but it's periodic. That is, once I come here and I come back again, I'm in the same place, and I get the same place over and over and over again. This, to me, is, I mean, I believe it. I'm incredibly surprised at this. That you have this, you know, we've been talking here, I think you've been talking here about rough energy landscapes. Well, this is a rough energy landscape, yet this is a property of rough energy landscapes that all of these things somehow, very, very rapidly, find a periodic thing to fall into. I don't know where that is written to be expected. I mean, I find that I mean, why should that be? And so I can tell you facts about this, but I don't have any sense of understanding of, well, what's going on? What is the nature of this rough energy landscape that we landed someplace, and that someplace is clearly not periodic, but after just a few cycles, it becomes periodic. Okay, so that's the thing that I wanted to show, and for this, and of course on this also, I want to got my line. Yeah, I mean, as I don't know how to answer that one, Eric. Okay, so this is bullshit line. And so why do I like this? I mean, all the rest of this stuff I think are facts. I mean, there's based on simulations, I think fairly decent reasoning. It's all there. What do I want to now say about this that makes this a little bit different? So what went into this? Very little. All we did was we cyclically forced a system over and over again at the same forcing over and over again. Have we seen that before? Yeah. The sun comes up at the same time every day. The moon goes around the earth same time every month. Every year we get winter. We have these cyclical things that keep forcing us over and over again. We wake up and the lights go on in the room at the same time every day. And my heart beats more or less at the same rhythm, or my breathing is at the same rate. These are all cyclical things that go on and over and over and over again. And we have all this amorphous material right here. And I keep wondering, well, if I listened to this very carefully, if I knew how to listen, would it have a memory of all those forcings in it? Is it just that, are these memories all stored for us somehow in the materials around us? So I find that a kind of a fascinating thing. We didn't use very much in here to get this thing to be, what did we use for the memories? It was just that it was cyclically forced. And so that's one thing. And the other things, well, what I talked about was really very simple principles here. I mean, so the simple principles were, I didn't use much. I gave you two examples, one from a hard condensed matter system where it was originally discovered, and now from a soft condensed matter fluids system. And the same thing, the same analysis works in both cases, and you get the same basic phenomena. And so the question is this a generic thing? Is this something that is really a generic feature of materials and how materials store memory? The other thing I just want to say is, well, it's so simple that you have to ask, well, does biology use it? Right? I mean, so and so look, I don't want to claim that this is how, if I ask you, okay, what's your cell phone number? I mean, okay, it's 312 blah blah blah. I mean, I can. I'm not saying that this kind of memory tells you anything about that kind of thing that you want to remember. But there are other kinds of memory that biology uses, and I want to give one example which feels right, and so it's definitely way below this bullshit line. But I mean, it's there. Is that suppose you're trying to learn a piece on the piano, and you've got this thing where you've got to do an octave. Well, what do? You put your fingers here, you wait an hour, okay, I've learned that one, and now I go here, and I sit there for an hour, and I learn that one, and now I've got it. No, what you do is you do this over and over and over and over again until it's in your muscles, right? And so the question is, so if this does apply to anything biological, then the question is this somehow inherent in muscle memories? And so this is the where I would try to say, oh, this is maybe where this kind of memory fits into this whole scheme of memories that we have. And there's not one memory fits all, but this is definitely one kind of a memory. Okay. Are there any questions?
I have a question about this graph. So for intermediate gamma value, the 0.07, you have this like two power laws kind of. This one.
Oh, okay. That I would claim is within this one here.
No, that on C. Yeah, right there. So around 15 seconds, slope changes. Right?
Yeah, I don't particularly believe that. I think that's within the noise of this thing. That is, those are not those are not straight lines. Those are just to fit the data. I mean, eyes to guide the eye. So that's not something I would put any. Georgia. I mean, hole burning is a different, certainly that's a different kind of memory. I don't know if it's related to this. I wouldn't have put it in this category, but it's definitely a kind of memory. There are lots of different kinds of memory that, that one has. Well, no, the thing is I'm not burning out that hole in a way. That is, you know, I'm basically erasing everything below a certain amount. So it's not, to me it doesn't, I mean, there can, I mean, look, there's some ways in which you can say, oh, there's overlap between these different concepts. I don't mean to say that there isn't, but it doesn't seem to me to have that same feel as this. It doesn't have that forgetting aspect of it if I do too much, for example. Okay, so look, I'm way, I blew this. I was going to, this was supposed to have ended half an hour ago. And I was going to do something else, which was about glasses. But since I'm clearly not going to be able to do very much on that, I want to do one other thing then. And so I'll just, sorry. So this is a sheet of paper, right? No. Okay. Okay. Who's the strongest person in the room? Okay. Can you squeeze it as hard as you can? Okay. How big is it? Don't ask me to catch it. Oh, I did. I caught it. Look at that. So look at that. So she's pretty strong. She's the strongest person in the room, and this is about a, you know, inch and a half in diameter, something like this. So what was she having trouble squeezing? This is 75% air, right? I mean, so you know, and the rest of you who are weaker won't get it much higher than this either, right? I mean, this is not. She did as best as she could, and it's still 75% air. So the question is there physics in this? And is this a marginal experiment? And I want to argue that it is, and that it's a marginal experiment that has things associated with memory and has things associated with glassiness in it. Okay, so who wants to try harder on this? Okay, so whoops. Okay, so so what was the? I mean, so one of the issues with this was, you know, where people started to think about this was. Let's see, did I? Let's see. Let me just. I got this. Okay. What was the experiment that? Well, so there was this experiment, and you know that hard as you try, it's 75% air, and so what's holding it apart? And so this has to do with, well, what is the nature of crumpling? That is, so you crumple something, and what's giving rise to that force that's not letting it get, you know, really tight? And it's the fact that you have this thin sheet, and you know it has. When you take that thin sheet, you can, you know, how do I do this? So if you have a sheet like this, you know, you're going to get points where this thing crumples, and between these crumples, you're going to get areas where you now have these two singularities, and you have a ridge between them, and you can ask, okay, so what's holding up giving you the force on this? And it's the ability to bend these ridges, which turns out to be the crucial thing that comes into this. So all of that was kind of worked out, but that has nothing to do with marginality, in a sense. So the issue that we did was, well, we took a did I show this? Yeah, okay, good. So what we did was we took a enormous sheet of mylar. So mylar is a very thin plastic, aluminized mylar, so it's very large. And we had a cylinder about this big, and we crumpled this cylinder. It didn't matter how we crumpled it, we just got it in there. And then we put a weight on top of this. And so I had an undergraduate student doing this, and so they put the weight on top. And so then I wanted to find out how much this thing was going to crumple as a function of the force. So she went and she measured the height of this thing and entered it into her lab book. And then, as a good experimentalist, she went to check that she entered the right thing. And no, she entered the wrong thing. So she had to erase this thing and put the new number in. And now she checked again to see whether she had gotten the right number. And no, she made a mistake again. So she took a little longer to erase this thing and put the new one in, et cetera, et cetera. So what she had discovered was that this thing didn't have a simple behavior. That is, if you start looking at this thing and you just put a weight on this crumpled material, it doesn't have a fixed height. This height just slowly decreases in time. And that's what this thing is showing you. So this was the Mylar experiment where we went for 1 million seconds. And so you have to get a lab that doesn't have air currents in it, so that's screwing things up, or vibration, so you put it on an optical table. But aside from that, all we did was have a camera on this thing, taking pictures at the beginning often, but then after a while, once a day is plenty. And what you see is that the height is just decreasing logarithmically in time. Okay, so that's where did that come from? What's the physics behind that logarithmic decrease in time? We're all taught that the only interesting thing in life is power laws, right? You're all theorists. That's what I was taught. Ever since I was introduced to theorists, that's what I was taught was the important thing, right? And I never, as an experimentalist, I never particularly bought that. But here, the important thing is that we had this very, 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 very slow relaxation, this logarithmic time dependence. What else could we do? Well, so we had this mass on a string, and it comes down, and roughly at 25 or 30 seconds, it pulled up on the weight so that the weight could no longer continue to compress this thing. And so this thing stopped moving, and it was no longer able to exert any force downwards on this thing. And then after 100 seconds, or 200 seconds, we released this thing. And now you look and see what the height does. It didn't care whether this thing was compressing it anymore. It just very quickly finds where it should have been and then continues on from there, right? So this was somehow another feature of this. And then, there's this issue of hysteresis in this case. And so if you really want to measure something that's reproducible, so there's a problem with these kinds of experiments is if everything is irreproducible, what should I tell you, right? That's the fundamental problem with that density tube that passed around. That is, if I want to tell you, if I can't tell you the density of sand, what am I supposed to tell you about this thing? What is the reproducible thing that I can give it to you? Do I have to tell you everything about how it was prepared before I even pass this thing around? Or what things are important and what things not? Those are some of the issues that come into this. And so what we tried to do here was try and see whether we could get a reproducible behavior. And so what we do here is now we do that thing, but with the first time, so we put the paper into this cylinder. We put a weight on it that which was at I think 2.5 kilograms, and let it sit there for a while. And so it was tried to get where it wanted to go. And then we took it off, and as we took off these weights little by little, we could see going back up, or the circles, and you come back down, and you get reproducible data. It reverses itself over and over again. But and you can do this over and over again, and you get reproducible data. And so, up to that log correction. I mean, so it isn't as if things aren't still moving a little bit, but within the scale of this, that is over the time scale that we were willing to wait, it was reproducible. But then, if we go past that, then suddenly this whole thing changes, and you now find a new curve. So now we went up to 5 kilograms, so twice that weight, and you got into a new curve, and now you go back and forth, and you find that the initial backwards curve is very different from the one that you had before. That it's learned a new thing. It has a new memory of where it was stored. And this one won't go back and forth on top of itself until it's been trained enough to do that. So there are various cycles that you have to go through before this becomes a reproducible curve. And then you can increase the curve more and more and more. And so this is the way of trying to figure out, OK, what does this height look like as a function of mass? And is there any power law or good functional form that will tell you how the mass relates to its volume, or the height relates to the forces on this system. So this is where it stood for a long time. And then very recently, the reason why I'm bringing it up now is that there are some very nice measurements that have come out of the Harvard group of Shmuel Rubinstein and his postdoc, I think, Yoav Lahini, and I'm not sure who Gottesman is, but Ariel Amir is a theorist there. And so this has just come out recently. And what they showed was that this thing really has a lot of the features. Not only is this the slow relaxation, which is somehow a hallmark of glasses, but this very simple system of just this crumpled paper has all of the kinds of waiting time dependence that you've probably heard about in some of the lectures here. That is, if you wait for a certain time under a certain load, this thing somehow will be able to reproduce for you how long it's been held at that new state. And so what was the experiment was, well, you put a mass on, and so this was, started off at 0. You put a mass on, and you let it wait here for a t waiting. And then you drop the mass to a different value, and you measure, let's say, the height of this thing as a function of time after this. So this is just the time scale. So you wait for a time t waiting, and you let this thing evolve. And that's what this is showing you, is that you get now non-monotonic behavior. That is, at the beginning, after you've released some of the mass on this thing, so it's going to try to expand for a bit, and then it starts to decay. And so it's got both the plus and the minus in here. It remembers that it originally was here, that you put a lot of force on to get it to this point, and now that I'm in here, it's remembering both that it's compressed over what it originally was and decompress over this, and those time scales compete with each other, and depending on how long you wait, this curve evolves with that. And so this is, again, one of the classic experiments in glassy physics where you see this waiting time dependence on how this thing was trained. Eric?
If you cut the paper, the crumple in half, would both pieces do this?
I'm doing this, you mean I'm putting 2 pieces of paper in at the first time, or I'm somehow...
So you put in 1 piece of paper, right, you crumple it, and then say you take a laser cutter and just slice it into 2 chunks.
I would, look, so I don't know, so I'll leave the experiment to you, Eric, but aside from that, I mean, my guess is, and so there's only a guess, is that you're perturbing this thing. That part of the thing is that there are forces at that point, and so that's going to relax things that will happen rapidly. It's as if you suddenly took off that weight at the top. And so you will see, I mean, so maybe what you're asking is, instead of releasing this thing, instead of this release, you just cut it at that point. And I would say that that's kind of like releasing the weight, and that there would be a waiting time for how long you let it sit before you cut it. Is that the question?
Well, I was thinking you release it and then you cut it. It doesn't really behave like a material, right? If you took a glass, you cracked the glass, you know, the piece of glass in half, both pieces would still have the memory.
Mm-hmm.
So does the crumpled paper behave like a material?
I would think it does. That would be my guess. That is, both of the whole thing is that there are going to be little bits in both parts which are trying to relax themselves, and so the stress is throughout this system. And I'm sure you can cut it in such a way that you've mangled this description, but just as a generic cut, I would think it would be the same kind of thing. Okay, so yeah. Well, so it will eventually, the forces will try to go to 0. That is, and so the way they go to 0 is presumably this logarithmic thing that I showed you on the first slide here, right? So there's a logarithmic time dependence to this. But what this experiment did was to look in that logarithmic time dependence, could you see something about how some relaxation events were happening faster and others slower, and the system somehow remembered them. So the final thing is still the same distribution of relaxations that I showed you with the log dependence. And so I expect that the log dependence will be what the eventual shape of this thing would look like. Long time. Okay, so I'm out of time. I'm sorry I didn't get to tell you about all the other things that I wanted to tell you about, but I got too excited. And so I apologize for that, but it's been a pleasure, and thank you very much.